Natural satellites are the moons which orbit the planets of the universe. There are nearly 200 confirmed moons orbiting planets in the solar system alone, with probably dozens more undiscovered. Satellites lurking at the distant edges of the Kuiper belt, the 6 outermost of the 8 planets, each have at least one natural satellite. Like our moon and the 4 gas giant planets each have dozens. With this many satellites which vastly outnumber the planets of the solar system, it's more than likely that the many billions of planets in the Milky Way galaxy are home to at least one natural satellite, from small asteroids to large Jupiter-like moons. But while their numbers are expected to be many, we've yet to actually confirm their existence by seeing one. As our technology for detecting planets in the galaxy has improved, the focus has begun shifting towards attempting to identify the moons around these remote worlds, which if confirmed would completely bolster the list of places in the universe which might be habitable to life as we know it. But we still haven't found them yet, and as such the hunt for the galaxy's exo-moons is ongoing. An exo-moon is the shorthand for extra-solar moon, any natural satellite orbiting a planet beyond the solar system. In the last decade we have discovered thousands of extrasolar planets around stars in the Milky Way, and one thing we've noticed is that our solar system is fairly typical. And so if other star systems in the galaxy are like ours, where there are planets there should be exo-moons. We predict that there are billions if not trillions of moons orbiting exoplanets out there, and they are expected to outnumber planets in our galaxy at least tenfold if these exo-moons are anything like moons such as Enceladus, Europa and Titan. Then they present a myriad of destinations for habitable rocky worlds orbiting planets similar to Jupiter or Saturn. But the problem is we can't actually see them. We have never identified an exomoon because satellites like the ones in our solar system are just too tiny and dark to be seen from hundreds or even thousands of light years across space. Current technology is enabling us to scratch the surface of the planetary systems orbiting stars, but their small dark moons are just a step too far for present-day technology. Therefore exomoon study is almost entirely dictated by the common traits we can infer from studying the moons in our solar system. All of the gas giant planets in the solar system have at least a dozen moons, and this number seems to increase with the size and mass of the planet, given that the vast majority of exoplanets we have detected are gas giant planets like Saturn, Jupiter, Uranus, and Neptune. You'd expect many of these exoplanets to house rich, diverse collections of natural and perhaps unnatural satellites. The vast majority of these probably resemble the moons we see today. However, when taking into account the inconceivable number of planets in the known universe, we can also probably expect to find some weird and wonderful variances. In addition to forming naturally around the parent planet, some moons may be captured worlds like Neptune's moon of Triton, or they could even be rogue planets which have fallen into orbit around a particularly massive gas giant while passing through its star system. This could allow for satellites far larger than the ones in our solar system, moons with atmospheres, magnetic fields, and even water. Exo-moons could be found within the habitable zone of their respected star systems all over the galaxy, potentially giving rise to dozens of small worlds with their own habitable properties around exoplanets, perhaps with sufficiently massive satellites boasting conditions analogous to those we enjoy on Earth today. But as mentioned, these are all just ideas, due to the fact that we've never seen one up close. But why is this? Well, detecting exo-moons from interstellar space is an enormous challenge. Direct imaging, which is the process of simply pointing a telescope at the star and hoping for the best, is just not feasible here. Not only do the immense distances render small satellite bodies virtually invisible to even the sharpest of telescopes, but the staunch differences in luminosity between the host star and parent planet obscures the satellites as well. So, instead of searching for one directly, another thing we could do is search for any signatures that the exomoon produces. For example, when Jupiter's moon of Io crosses through the lines of Jupiter's magnetosphere, a powerful frictional current is created around it that emits radio waves. Such a signal would be easier to detect than an impossibly small dot, but it is still just the wrong side of mankind's technology. One method which is widely used for this sort of thing is to take measurements of radial velocity. This method, also known as Doppler spectroscopy, or the wobble method, is the process of analyzing a star's spectrum to detect signs of something acting upon it. Just as a star is always exerting a gravitational influence on the planets orbiting around it, those planets create their own very minor counter-movement in the star, a reverse wobble. If this occurs within a star system that we are observing, then the radial velocity of the star, that is the rate of change in distance between it and us, will vary periodically. This slight back and forth movement relative to us is detectable as redshift and blueshift lines in the star's spectral data. Such lines are evidence of a planet in the system. This method has helped us to identify no less than 880 exoplanets to date, approximately 1/5 of all discovered. As spectroscopy technology improves, one hope is that we may be able to begin analyzing planets for similar signatures of moons as they cause the planet to wobble. But we are still a considerable way off the technical capacity to be able to detect something so incredibly subtle. This method also requires the star in question's orbital plane to be aligned with our line of sight on the Earth, so that the counter motion of the star moves it backwards and forwards to create the Doppler shift lines. So in reality, this rules out a large class of exoplanets out there, as well as their exomoons, because most will simply not have their planes aligned with us. Unfortunately, when we analyze distant star systems, we more often than not need the parent planet to give us some clues. This brings us to the next method of exomoon detection, the transit method. This is the same method we use to detect most of the known exoplanets, and is generally the most reliable method when it comes to detecting things around stars. This can be performed when an exoplanet passes in front of its parent star relative to the Earth. When this happens, the light being emitted from that star is ever so slightly dimmed as the planet passes in front, blocking out a small section. This is a great way to detect planets orbiting stars, and it even enables us to reverse engineer some of the planet's characteristics, including the distance from its parent star and thus estimations of its size and mass. We detect the dimming caused by these planets as small variations in the measurements of a star's light curve, and so it is possible that exomoon signatures could also be extrapolated from the data, because the dimming of a star is proportional to the radius of the transiting object. A planet-moon system which is passing in front of its parent would block out more light than just a planet. In addition, the presence of a sufficiently massive exomoon would slightly delay the timing of the transit, as the very center of the system is tugged back by the satellite's gravitational influence. Such a motion would produce an exomoon signature known as a transit timing variation, but these could just as easily be caused by hidden planets elsewhere in the star system which are acting on the orbit of the planet under observation. Nevertheless, data from the Kepler mission, which ended in 2018, has been used to identify a handful of exomoon candidates, but today none of these have been confirmed. The main driving force behind uncovering these satellite signs is the hunt for exomoons with Kepler project, founded by British exomonologist David Kipping, whose aim is to identify exomoon signatures from the mission's data for further observation. The HEK uses transit timing variations in measurements of radial velocity to identify a potential exomoon targets. The project has submitted no less than 6 papers suggesting candidates in the last 9 years, with the most promising candidate coming in 2017, Kepler 1625 by Kepler 1625 is one of the many stars observed by the Kepler instruments since 2009. It lies about 8,000 light-years from the Earth in the constellation of Cygnus. It has a similar mass to our Sun but is about 70 larger owing to its more mature phase at 8.7 billion years old, while the full extent of its planetary system is probably larger. We have identified one planet orbiting the star, denoted as Kepler 1625b. It takes roughly 8 months to orbit, so we are quite restricted in when we can study it. We recorded 3 transits of the planet between 2009 and 2013, and what we have managed to ascertain is that the planet is probably a super Jupiter, similar in diameter to our largest planet but several times more massive. This planet was identified as a candidate exoplanet in 2015 and it was verified in the following year. But some say that the data suggests more than an exoplanet in the vicinity, rather a planet-moon system. The HEK analyzed the transit data recorded and uncovered 2 inconsistencies, perhaps consistent with the signature of an exo-moon. The first was a transit timing variation. The planet's transit of the star was delayed slightly, most likely by another gravitational influence pulling on it. In addition, they also found that just over 3 hours after one of the 19-hour transits ended, another flicker caused by a slight dimming was detected, consistent with a large moon trailing the planet a distance, like a dog following its owner in the absence of instrumental or data processing anomalies. Kipping argues that an exomoon hypothesis is the simplest and most fitting explanation, and the only one which fits both scenarios. The thing is, if this is a moon, then it would be a fairly atypical one. In order to explain the flicker, the exomoon's diameter would have to be around 3.5 times the Earth, making it only slightly smaller than Neptune with probably around 30 times the Earth's mass. At this size is unlikely to be a rocky moon, rather it is probably a gas giant moon. But gas giants do not form as natural satellites around planets, and so the satellite must have arrived by some other means. It is most likely a captured world like Triton which began life elsewhere in the system before being pulled into orbit around a larger body. The Canada exomoon, dubbed Kepler 1625b, appears to orbit about 3 million kilometers away from its parent planet, which could be indicative of the moon once being pulled into a wide-angle orbit by the intense gravity of Kepler 1625b, far greater than even the power of Jupiter, and so able to exert a vice-like grip over the rest of its system. If the satellite was once a Neptune-sized planet in its own right, then we would expect it to have its own system of moons. But if they are anything like the small, icy moons of Uranus and Neptune, they would be impossible to detect. However, if any are still with the captured giant, as it orbits the super Jupiter today, then it would be a moon of a moon or a sub-satellite. But then that's getting a bit ahead of ourselves, speculating on the moons of a moon we don't even know exists yet. If it was to be confirmed, then Kepler 1625b would be the first known gas giant moon. But that's quite a big if, as the evidence is far from conclusive. The star system has since been observed using the Hubble telescope, after being allocated a preliminary 40-hour slot. Unfortunately, these 40 hours did not fall on a time in which the planet was in transit of the star, and so we still need to use the telescope to make more extensive observations before we can conclude. Furthermore, a recent independent study found that a planet-only model with no moons fits the data recorded from Kepler 1625 better than a planet-moon model. They suggest that the transit signal of the moon is merely an artifact of the data reduction, and that there is no significant evidence for the moon's existence. Many more transit observations will need to be made before we can get any closer. But sadly, the technology to do so is just out of reach, and so for now, Kepler 1625b remains a boring name, but a fascinating exomoon candidate nonetheless. With question marks over the former, what other exomoon candidates have we got on the watch list? Well, MOA 2011 BLG 262 is one of the main ones. This planet-moon system was proposed in 2013, modeled as a moon less massive than the Earth orbiting a gas giant planet. several times the mass of Jupiter within the galactic bulge area of the Milky Way. Unlike other examine candidates, MOA 2011 was identified not by transit timings, but by microlensing. Microlensing occurs around large dark bodies in space, as light is slightly warped by their gravitational fields as it travels towards us. This is a good way to detect free-floating rogue planets barreling around the Milky Way's darkest recesses. And this is what is being proposed, a rogue planet-moon system. But with that said, the data is also fit by a model of a brown dwarf with a planet system, a faint failed star circled by a planet 18 times the mass of the Earth, and not an exomoon, because our observations are little more than relative guesswork at this point. It is impossible to say which could be the case at the moment, but perhaps in the future more advanced microlensing could help us to uncover those planets we cannot see through transit and radial velocity measurements. Speaking of transit measurements, earlier this year no less than 6 new exo-moon candidates were proposed by the HEK, all identified via transit timing inconsistencies around their parents' star. However, a recent independent study reviewed each candidate, validating each via 3 rigorous tests. For transiting exo-moons, 1 are there significant excess transit timing variations, 2 is there a significant periodic variation, and 3 is there mathematical evidence for a moon's mass causing these variations. Under these tests, 2 candidates were ruled to be more likely the result of interactions with other hidden planets, and each of the other 4 candidates only passed a maximum of 1 test out of the 3, so it's hardly indisputable. That same review also found that Kepler 1625b passes 2 out of the 3 tests so far. Now it would seem it remains our best hope of finding an exomoon. Music. The infuriating yet tantalizing thing about exo-moons is that they are just not attainable to us yet. They are too small, dark and hidden, but our technology to find them is merely in the fledgling stage. So while it is too early currently to hope for confirmation, it is more than likely something we can look forward to more coverage and research into. In the near future, we've finally broken the ice with these emerging candidates, and before long we will probably have dozens of them, and sooner or later we're bound to come across that one which makes it all real. And once it does, it opens the door to trillions of new habitable worlds in the cosmos, and loads of new places to think about. The emergence of life in space exploration destinations like the James Webb Telescope, which is due to launch late in 2021, will help us to improve our search techniques. Having been delayed for so long, it has a lot of expectation riding on it, but once it does finally launch, it will reveal space to us in pristine new detail, perhaps finally helping us to identify the bewildering numbers of exo-moons out there. We've already pondered the idea of a gas giant moon, so just think what could lie elsewhere in the vast universe, let alone in our local galaxy. Perhaps when we are able to get closer, we will discover moons beyond the solar system. They're even more weird and wonderful.